Let's talk about the implicit differentiation for multivariable functions in this lecture. Suppose we have a two-variable function that is in this form. So all the non-zero terms are on the left-hand side, so we have f of x and y, and the function equals to 0. And since we have an equation of two variables, so we can also say that y is implicitly defined as a function of x. So I can rewrite the original function as f, the function, as a function of x and f of x, and thus equals to 0. Then using what we just learned from the previous lecture, let's draw a tree diagram. So we have the function f, that is a function of x and y, where y is implicitly defined as a function of x. So y is function of x. So the derivative of f with respect to x, if we look at the end of this tree, we have an x here and an x here. So this also equals the partial derivative of f with respect to x, then times dx over dx, plus, along the other branch, I have the partial derivative of f with respect to y, then times dy over dx. And since we have the function f that equals to 0, so its derivative should also be 0 since the function is a constant, so this should equal to 0. And what we want to isolate is the dy over dx, derivative of y with respect to x. So we can isolate this term from this equation here. Another note is we know dx over dx, this equals to 1. So dy over dx equals negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. Or we can abbreviate that as the negative of the function sub x over function sub y. And now we get to an equation of the derivative of y with respect to x. How about if we have an equation that involves three variables? We can do the similar approach. So we put all the non-zero terms to one side. So we have an equation that is a function of x, y, and z equals to 0. Then I can say that z is basically a function of x and y. So I define a function f, that is function of x and y, and let z equals to that function. And what I want to find is the partial derivative of z with respect to x and with respect to y. Let's draw a tree diagram for this function. So initially I have the function f, that is a function of x, y, and z. And since this equals to a constant, so I can basically solve for z and rewrite z as a function of x and y. So I can define z as function of x and y. So if you want to get the partial derivative of f with respect to x, then I get df over dx and times dx over dx, then plus df over dy times dy over dx. And the last variable is the z, so df over dz times dz over dx. And since the function f equals to a constant, the function equals to 0, so its derivative with respect to any variable should be 0. Then I can solve for this part, dz over dx. And I also know that dx over dx equals to 1 and dy over dx equals to 0. Since from the tree diagram, y is not function of x, so its derivative with respect to x is 0. So I can solve for dz over dx. It equals the negative of df over dx over df over dz. Or we can abbreviate that as negative of f sub x over f sub z. Similarly, we can take the derivative of the function with respect to y, and we will get to a similar form. we will get that the partial derivative of c with respect to y equals negative of the partial derivative of f with respect to y over the partial derivative of f with respect to z. Or we can rewrite that as the negative of f sub y over f sub z. Now let's look at two examples using the equation that we just derived. So the first one, we want to find the y prime if the equation is x cubed plus y cubed equals to 6 times x times y. So this equation involves two variables, x and y. So I can define my function f as function of x and y. And to use the equations that we just derived, I need to have this function equals to 0. So I need to move the 6 times x times y to the left-hand side. So I define the function as x cubed plus y cubed minus 6 times x times y. And this equals to 0. Then I can use the equation that we derived. So the derivative of y with respect to x, it would be the negative of partial derivative of f with respect to x over the partial derivative of the function with respect to y. So this equals negative, in the numerator I have 3 times x squared minus 6y. Then over f sub y, that is 3 times y squared minus 6x. I can factor out the 3 from both the numerator and the denominator. So this equals negative of x squared minus 2 times y over y squared minus 2 times x. Now let's look at the second example. We want to find the partial derivatives of z with respect to x and y if we have the equation x cubed plus y cubed plus z cubed, then plus 6x times y times z. And this equals to 1. We can see that this equation involves three variables, x, y, and z. So I can define my function f of x, y, and z as the equation, the left-hand side minus the right-hand side. So the function equals to 0. But you can also note that the right-hand side of this function is a constant. So even if I don't move the 1 to the left-hand side, I can still use the equation that I just derived. But let's make everything consistent. So let's put all the non-zero terms to the left-hand side. And I get x cubed plus y cubed plus z cubed, then plus 6x times yz, then minus 1. So this function equals to 0. Then I can use the equation that we derived. I can easily write out the partial derivative of z with respect to x. It is the negative of f sub x over f sub z. So this equals negative of the numerator f sub x, that equals to 3 times x squared plus 6 times yz. Then over f sub z, that's 3 times z squared plus 6 times x times y. I can cancel out the 3, so this equals negative of x squared plus 2 times yz. Then over z squared plus 2 times xy. Similarly, for the other partial derivative, dz over dy, it equals to negative of f sub y over f sub z. F sub y is 3 times y squared plus 6 times xz. And the denominator is the same, the f sub z. So 3 times c squared plus 6 times xy. Similarly, I can cancel out the 3. So this equals negative of y squared plus 2 times xz, then over c squared plus 2 times xy. And that is the end of the lecture. So in this lecture, we learned that when we have an equation that involves 2 or 3 variables, I can easily find the partial derivative of one of the variable in terms of the other variables by letting a function that equals to 0, and we've derived the partial derivatives of the variable with respect to the other two variables. In the next lecture, let's talk about the gradient vector and the directional derivatives.